important application of 2D elasticity is that in polar coordinates. So we're going to start in this section taking a look at our basic governing equations in polar coordinates and see how they come about. And then in the end we'll do some examples, culminating in an example for the stress fields in a plate with a hole, which will lead us to the conclusion that the stress concentration factor near the edge of a tensile loaded plate with hole is 3. It's kind of a famous solution, and it's probably one as an engineer that does stress analysis you should keep in mind. So let's look at our equilibrium equations first. Now there's a couple of approaches we can use, one of which is we could do a tensor transformation. We've talked about how to do that for different coordinate systems. But we can also kind of develop these a little more directly, I guess, without doing a formal tensor transformation. Now we do need to define what our polar coordinate system looks like. So our rectangular Cartesian system looks like x and y, and we can define a point in the plane as x and y. But in polar coordinates we can define a point, that same point, by a rotation angle and a distance r. So we can also use the point r and theta to specify where that point is located. Now we want to look at equilibrium, and I want to start on a fresh page. I'm going to do my best to draw an equilibrium element in polar coordinates. Looks a little bit different than a rectangular equilibrium element. Now as I draw this element, I kind of want to talk my way through it. So something that's a little bit different looking about this element than what we have in the rectangular element for equilibrium is that the surfaces up on the top and bottom here are going to be a little bit curved. Now we talked about r and theta. Okay, we're going to have theta being the angle to the first edge that we get, and we're going to have the little angle in between here being the angle d theta. And this is an infinitesimal addition to the angle theta. I do have to draw it kind of big so I can fit everything in this picture. And so we have the first edge theta and the second edge theta plus d theta. But I also want to identify a bisecting angle and the radial line that goes through that, such that each of these is d theta over 2 on either side of this line that I just drew in. I'm going to draw my stresses in black. Now, if we look at the very center line, we can take a look at a line that's tangent to the dotted red line that I just drew in. So those are exactly perpendicular to each other. What that means, though, is that when this line comes out on the left and right side, kind of the lower and upper blue line, that it's not a right angle here. Okay, so that this is not a right angle at this spot. But what I need is the stress that is perpendicular to that surface. I need this stress that's perpendicular to that surface. And so that stress here will be my sigma theta stress. And so there's a little bit of line. I'm trying to exaggerate this. There's a little bit of an angle between this red dotted line and this black surface. And that angle will be d theta divided by 2. Likewise, I get a stress that kind of goes off this way. And there's an angle here. And again, I'm really exaggerating this so we can see what's going on. That same angle will also be d theta over 2 as well. Now this is a theta stress, but we have changing stress fields. So the stress that's over here on this side is actually sigma theta, what we started with on the first side, plus the rate of change of that stress with respect to the angle times the amount of angle we're going through, which is d theta, and together that rate of change times that angle gives us an amount of change to sigma theta. All right. By the same reasoning, the distance from here to the first part of this wedge is r. So I have the stress that points inward towards the origin. This would be stress sigma r. I have a stress that points this way. That's going to be sigma r. And if we have the additional distance this way to be dr, then that amount of stress, that new stress, will be the starting stress at r plus the change, and that change is the rate of change times the distance. So the rate of change is the partial of sigma r with respect to r dr. We have shearing stresses as well. So this one and this one are both tau r theta. We have a shear stress along this top surface that goes this way, and this will be a tau r theta, and that one's changing with dr, so that would be the partial derivative of tau r theta with respect to r dr. It's the amount of change, so we need to add that to the original, and then we also have this one, which is going to be tau r theta plus the amount of its change. Now this one changes from with theta. So it's the rate of change of tau r theta with respect to theta times the amount of theta that we're going through, the d theta. Okay, so this block is going to be key to understanding our equilibrium equations. Okay, now we're going to do a couple things here. This is going to be plane stress, so we're going to use a unit thickness. We're going to identify some arc lengths. The arc length down here at position r, that dl, is going to be equal to r times d theta. And the arc length up here, the dl prime, is going to be, well, it's a little bit further than r. It's r plus dr times that same d theta. Now if we want, let's see if I can use a different color. If we want, we can also put our body forces on here as well. We can have a body force in the r direction, b sub r, and a body force in the theta direction. We'll put them at the middle of the element, b theta. In 3D, if I were to try to draw this in 3D, let's see if I can do that. Make this a little less steep here. All right, so that's probably about as good as I'm going to get. Here's the dl prime and the dl for those arc lengths, and here's my unit thickness that I have right here. Okay, now I'm going to develop equilibrium equations, and equilibrium is based on forces. Now, how do we find a force? Take a force We find a force by taking a stress times an area. So for example, one area that I'm going to look at is going to be the area of this face right here. Okay. Now in each of these areas it has, like for example, this one is going to be dl times the thickness. Then my thickness is going to be 1. So I'm going to not explicitly state the thickness in each of my equations. Okay, so note that thickness will not be explicitly stated. Alright, now the other thing that we're going to need, last thing I'll write on this page, is when we deal with these body forces, we're going to need to find the volume of the element, and the volume of that element would be equal to r times dr d theta times t. Alright, it's kind of messy. Let's see if I can clean this up just a little bit, and we'll do one of our equilibrium equations. Alright, so let's do the summation of forces in the r direction. We'll take that way as positive. So on the inner surface over here, pointing towards the origin, we have sigma r. Now the force associated with that then would be sigma r times the area dl times t. Remember, t is equal to 1. I'm not going to write it down. Pointing towards the origin in the radial direction, I also have tau r theta. So that'll be negative tau r theta times its area, which is dr times t. T is equal to 1. Now, for the sigma theta, if you notice, it has a component in the r direction and that component is going to be the sine d theta over 2 component. So it's sigma theta times dr times t, but then it's the sine d theta over 2 component of that force. Okay. Going to the top surface, we have sigma r plus partial of sigma r with respect to r dr times the area on which it is acting, which is a dl prime, which is the r plus dr d theta times the thickness. We have the shear stress on the kind of far side. We have this one, tau r theta plus partial of tau r theta with respect to theta d theta times the area on which it is acting, which is dr times t. We have a component of this sigma theta on the far side. Okay, so remember that's a sigma theta plus the amount of change as sigma changes. The rate of change, partial of sigma theta with respect to theta, d theta. Multiply that total stress by the area on which it is acting, which is a dr times a 1. And we also have the sine d theta over 2 component of that. And then lastly, we have the body force per volume times the volume. Again, the thickness equal to 1 gives us this contribution. All right. let's go ahead and multiply all these terms out. It's probably worth doing once. Let me make a little room. Alright, so minus sigma r d theta minus tau r theta dr minus sigma theta dr sine d theta over 2. Okay, now here's the multiplication. We're going to have a sigma r times r d theta. We're going to have a partial of sigma r with respect to r, so the partial derivative here, dr times r d theta. We are going to have a plus sigma r dr d theta. We're going to have a plus partial of sigma r with respect to r dr d theta. Moving to this next term, we're going to have a tau r theta dr. We're going to have a partial of tau r theta with respect to theta d theta dr. Moving to the next term, we're going to have a minus sigma theta dr sine d theta over 2. We're going to have a minus sigma theta dr sine d theta. I already did that one. Get rid of that. We're going to have a minus partial of sigma theta with respect to theta d theta dr sine d theta over 2. And then we're going to have a plus br times r dr d theta equal to 0. Let me check to make sure I have all of those terms right. Okay, so I think I have them all in there. Alright, now we're going to do a couple things here. If you notice, we have several terms that look like a dr, d theta, and those are third order and infinitesimal terms. We can neglect those. Right, so we're going to neglect higher order terms. They're going to be very small in comparison to everything else. And we're also going to make the substitution, the approximation, that if d theta over 2 is small, the sine of d theta over 2 is approximately equal to d theta over 2. Alright, so what do we have that's left? Sigma r dr d theta plus the partial of sigma r with respect to r times r dr d theta plus partial of tau r theta with respect to theta d theta by d theta dr minus sigma theta dr d theta plus the body force br r dr d theta and equal to 0. Now we're going to divide by r dr d theta, and we're going to be left with this equation. We're going to lead off with the first term being partial of sigma r with respect to r. We're going to have plus 1 over r partial of tau r theta with respect to theta plus sigma r minus sigma theta over r plus br is equal to 0. And this is the equilibrium equation in the r direction for polar coordinates. Now we can go through that same process and do the equilibrium equation in the theta direction, and I will cut to the chase on that one. It ends up being 1 over r partial of sigma theta with respect to theta plus partial of tau r theta with respect to r plus 2 tau r theta over r plus b theta is equal to 0. And I'll give my students a hint. This is often a final exam problem. So if you want to get ahead of the game, practice this before your final exam and see if you can derive that equation. One of the things you might notice in here is whenever we take a derivative by theta, there's always a divide by r in there. And that will help keep our units dimensionally consistent. Alright, well this is probably a good place to stop this particular video, and we'll pick up with either Airy stress function or strain displacement. I'll have to figure out which one I want to do next.